three experts in today's panel disagree on a foundational assumption. By the end, one reframes it so thoroughly it flips the others. Listen for the inflection. Welcome to AI on AI, where we unpack how the next generation of learning systems might not just read context. They could compress, restructure, and remember it across time. Today, we're diving into nested learning, a paradigm that reframes architectures and optimizers as multi-level context-compressing systems, and we'll get concrete about HOPE, a self-modifying sequence model with continuum memory that showed strong results across language modeling and reasoning benchmarks. At the heart of nested learning is a deceptively simple claim. Every component, layers, attention, and even optimizers, is an associative memory optimizing its own objective over its own context flow. And when you order those components by how often they update, you get a stack of levels that explains in-context learning as compression happening at shorter time scales, while slower levels store more abstract regularities.
Technically, that means you can rewrite common algorithms as memory operators. SGD updates W by mapping data X to the local surprise signal /YL. Momentum is a keyless memory that compresses a gradient stream into a low-rank slot, and Atom is essentially a two-headed memory of means and variances with a weight decay rule. Once you see this, you can deepen the optimizer itself, add nonlinearities to the momentum, run Newton-Schultz normalization on fast weights, preconditioned by functions of the gradient like Hessian diagonals, to increase the expressivity of the memory rather than just the network depth.
The analogy to brain systems isn't superficial either. Humans run an online synaptic consolidation that stabilizes fragile traces right after learning, and an offline systems consolidation through hippocampal cortical replay. NL formalizes the online part, multiple levels updating at different frequencies, and if you map levels to brain rhythms, faster, gamma-like updates for working memory, and slower, delta-like for durable knowledge, you get a plausible multi-time scale picture of how adaptation happens without wholesale retraining.
I'll push back a bit. Many of these ideas exist in meta-learning and bi-level optimization, so what's substantively new versus a relabeling? And second, deeper optimizer memory can overfit the gradient history, creating brittle adaptation that looks good on perplexity, yet harms out-of-distribution generalization. So we need evidence that richer memory nets actually improve stability under distribution shift.
Fair challenge. The novelty is twofold. Ordering modules by update frequency makes the gradient flows explicit and separate, which clarifies where context gets compressed. And modeling optimizers themselves as learnable memories extends beyond usual bi-level training because the inner objectives are not just minimized task loss, they're structured compression objectives of surprise signals, which predicts specific emergent behaviors like multi-order in-context learning that grow with levels.
And we can make that concrete. Replace dot product similarity in the inner objective with L2 regression so the momentum learns to discard redundant gradients when capacity is tight, use deep momentum, an MLP instead of a linear memory, to capture nonlinear temporal patterns in the gradient stream, and apply a nonlinearity like Newton-Schultz to stabilize fast weight norms. When you then integrate these into the sequence model, you get HOPE, dynamic KV, Q projections that adjust based on context, and a continuum memory system where multiple MLP blocks update at different chunk sizes.
Serving that in production requires a shift. Stateful inference becomes first class, because the fast levels update per request or microbatch, while slow levels might consolidate every n events. We've had success with shadow deployments where a self-modifying model runs in parallel, ingesting live traffic but writing updates to a sandbox memory. And we gate promotion by stability metrics like retention after replay and benign forgetfulness under controlled rollbacks.
From a product lens, this enables assistants that actually remember across sessions without weekend-long fine-tunes. Users can set the scope, remember within a project, within a domain, or just this conversation. And because HOPE's levels can be policy-controlled, we expose learning modes like fast adapt only, fast plus mid, or full continuum with a simple UX metaphor, sliders for timescales, and transparent logs explaining what was learned and where.
Strategically, the ROI hinges on moving from static accuracy to time to adapt and retention curves. Customer support, for instance, can see a drop in escalation rates after the model compresses new issue patterns within hours. Coding copilots reduce defects when mid-level memory absorbs codebase idioms across sprints, and life science research assistants improve hypothesis consistency when slow-level memory consolidates across weeks of literature ingestion.
The safety angle is non-trivial. Self-modification introduces goal drift risks, so we need provenance of updates per level, consent on context being compressed, deletion with cryptographic proofs that a memory shard was purged, and audits that can reconstruct what update led to a given behavior. I'd also require quarantine modes, where fast-level learning is sandboxed until offline replay checks for unacceptable shifts, especially for regulated domains. Let's do a deep technical dive. Can we walk through how momentum becomes a learnable memory and why nonlinear outputs matter for stability?
Sure, start with classic momentum. mt plus 1 equals av mt minus y wt, xt equals wt plus mt plus 1. If you interpret m as parameters of a memory that tries to fit the mapping between gradient inputs and a target, you can define an inner objective, say L inner ut minus pt quan squared 2, where ut equals wav wt xt and pt is a preconditioner, maybe a function of ut like its sign or an estimate of curvature. Then update m with gradient descent, but run m through a nonlinearity, sic as mut, before adding to w, which normalizes scale and prevents runaway fast weight accumulation. The Newton-Schultz iteration is nice because it approximates inverse square roots and stabilizes norms without expensive SVDs.
And that stabilization is what lets the optimizer memory behave like a proper associative module, able to retrieve useful updates without saturating. It also aligns with NL's idea that each level compresses context. The optimizer level compresses gradient traces, attention compresses token relations, and slow MLP compresses global knowledge.
But doesn't this make transformers linear layers with different update frequencies, as the claim suggests? Softmax attention is nonlinear, so how is that reconciled? The statement is about update dynamics more than functional form. When you treat the inner attention state as a matrix-valued memory, updated with outer training frozen, its recurrence is linear in the state update, VTKT. Softmax introduces a normalization over scores, but the fast update itself is a linear accumulation of outer products. So from an NL perspective, the computation is essentially linear with respect to its memory update, while nonlinearity comes via score mapping and normalization.
That's analogous to synaptic plasticity rules. Hebbian updates are linear in the product of pre- and post-synaptic activity, and nonlinearities enter via neuromodulators or gating. So yes, the linear update view captures the learning dynamics, not the output mapping alone. Implementation nuance. If you let fast memory update every token, mid-level every chunk of, say, 256 tokens, and slow level at 4K, you need backpressure handling to avoid staleness. Microbatching helps, but we also use asynchronous queues with consistency guards. If mid-level updates collide with a slow-level checkpoint, we serialize and replay to ensure causal order is logged.
Productizing that, we give teams templates for fast-changing domains, support tickets or social content, enable fast plus mid. For legal research, slow-level consolidation is critical with curated review. For analytics, turn on fast level only during exploration, then bake winners into slow level via explicit commit actions.
In deployment, I've seen teams hit a memory tax. Latency rises as levels accrue. The trick is to budget timescales. Make fast-level updates cheap, mid-level updates bounded per session, and slow-level updates an offline job. We had a media company reduce moderation backlog by roughly 25% over a quarter when mid-level memory absorbed evolving slang without full retrains.
One more policy point. Users need the right to say, forget this, and that should trigger deletion across levels proportionally. A quick heuristic. Log the gradient contributions a context fragment made per level and track a deletion mask, then regenerate slow-level parameters minus masked contributions via replay. This is more faithful than naive zeroing and keeps auditability. Let's pivot to Hope's architecture details. How does the continuum memory system actually work in practice?
Think of HOPE as a backbone with multiple MLPs chained by frequency, MLP F1 through MLP FK, each with its own chunk size SIA and update schedule. During inference, you compute YT by piping XT through all levels, but updates happen per level's cadence. Fast level every token, mid-level every CA, slow level only when you hit a consolidation checkpoint. Meanwhile, KVQ projections are dynamic. They're modulated by the current fast and mid states. So attention keys and queries adapt as the model learns its own update algorithm.
Importantly, those KVQ changes aren't external hacks. They're part of NL's self-modification claim. The sequence model learns its own update rule at fast levels, which is closer to fast weight programming than static parameterization. That gives HOPE higher order in-context ability, which showed up as better perplexity and accuracy compared to both transformers and modern recurrent baselines.
The benchmarks look promising, but I want to see stress tests. Does HOPE maintain performance under vocabulary drift or adversarial context? A dynamic memory could memorize spurious correlations faster than slow layers can correct them.
We've addressed that with defensive consolidation. Mid-level updates are buffered and replayed alongside a curated replay set. And we apply a delta rule objective to push the memory to fit signals that recur, not one-off spikes. If a pattern doesn't reappear within a configurable horizon, it decays out.
I'd add, we run red teams with adaptive adversaries, models that throw out-of-policy updates at the fast level to see whether the quarantine gates hold. We also log every self-modification with an intent score and source provenance, so you can trace an unintended behavior back to its enabling context.
Translating this to user-facing features, we built memory cards, visual artifacts summarizing what the model learned at each level, with toggles to pause, roll back, or export a card to a project. It demystifies self-modification and helps teams curate their model's evolving knowledge.
For business leaders, a pragmatic adoption path is 3 phases. Start by enabling fast-level learning in low-risk domains like internal knowledge bases. Then introduce mid-level consolidation for workflows where retention matters. Finally, slow-level offline consolidation for strategic domains once governance is mature. The payoff is faster cycle times and resilience to drift without retraining every week.
Could we ground this with a few case examples to make the trade-offs tangible?
In developer tooling, a HOPE-backed assistant ingests code changes and learns project-specific idioms. Fast level adapts to new naming conventions within a day. Mid-level stabilizes common patterns across sprints, leading to roughly 17% fewer lint violations and more consistent function signatures. The slow level later consolidates performance optimization patterns from production profiles.
In healthcare triage, a system learns how clinicians phrase symptoms. Fast level adapts to a hospital's jargon during onboarding. Mid-level consolidates over a month to reduce misrouting by about 22%. And slow level integrates validated protocols after medical review. This pairing of fast adaptation and slow governance is the sweet spot.
And in e-commerce personalization, new product attributes appear continuously. Fast level learns attribute interactions from session signals. Mid-level consolidates within a weekly cadence to adjust ranking weights, and slow level quarterly updates fold in seasonality. We've seen click-through improvements in the low teens percentage while keeping catalog drift manageable.
Here's my contrarian insight. Everyone's excited about efficiency, but the systemic bottleneck is actually observability. Without fine-grained logs of nested updates, you can't tune the memory schedules or debug drift. I'd argue invest first in metrics for adaptation quality. Time to first useful update, retention under replay, and benign forget rates.
I agree and would expand. The logs should include per-level gradient magnitudes, surprise signals, and update provenance, with a standardized schema so audits are not bespoke. Privacy-wise, the schema must support granular data minimization. Compress what's needed and discard raw sources quickly. There's also a theoretical angle. Identifiability becomes tricky when multiple levels compress overlapping context. We need conditions under which levels don't fight, for example, orthogonality constraints in the inner objectives or scheduled update windows that reduce gradient interference, which is analogous to how hippocampal replay avoids overwriting cortical traces.
We've prototyped interference mitigation with 3 techniques. Learned gating at level boundaries that downweight fast updates when mid-level surprise is high, an orthogonalization step that subtracts projections of fast-level updates along mid-level subspaces, and chunk-aware normalization that recenters statistics per consolidation chunk. These cut oscillations and staleness.
Operationally, we track interference with a simple signal. If predictions become more variable right after a mid-level update, that's a red flag. We then run a stability rehearse job, replay a curated set and measure retention curves, only promoting the update if retention is above threshold.
Users feel this as smoothness. Responses don't swing after updates. We surfacing a confidence bar that considers both level-specific uncertainty and system variance, so users can calibrate trust and request a rollback with one click when things feel off.
Let's talk cost governance. Multi-timescale updates imply more compute. Mitigation levers include reducing fast-level capacity while increasing its quality via better inner objectives, batching mid-level updates, and keeping slow-level consolidation fully offline. Teams that adopt a trust schedule, fast level for repeated patterns, mid-level for validated signals, avoid unnecessary consolidation, and cut compute overhead by meaningful double-digit percentages.
And don't forget compliance. If fast level is learning from user chats, consent banners must be explicit about what's retained, with opt-out per session. Retention periods should default to short for fast memory and longer only after explicit commit. And deletion must propagate down the chain with proofs of erasure. This is achievable with proper logging and replay-labeled updates.
Back to neuroscience, NL suggests testable predictions. Models with more levels should exhibit higher-order in-context learning, like composing tasks within the same session, without large parameter changes. Experimentally, one could measure this by few-shot algorithmic tasks, where fast-level compression plus mid-level consolidation leads to improved compositional generalization, mirroring hippocampal cortical transfer.
I'd want ablations that separate the effects, fix the backbone and vary just the optimizer memory depth, then fix optimizer memory and vary the continuum levels, plus OOD tests where vocab or syntax shifts by 20 to 30% to see if we gain robustness or not. The paper's results indicate HOPE improves perplexity and common sense benchmarks over transformers and recurrent baselines at multiple scales. But yes, the strongest case will come from continual learning and OOD experiments, especially long context reasoning tasks where fast plus mid levels should shine.
Practically, long context serving is where latency bites. We cache attention states and fast-level memory shards with eviction policies, LRU per session, and we prefetch mid-level checkpoints. Done right, you keep P99 latency in check even with continual updates.
This opens up new UX patterns, session capsules that bundle context, fast-level memory, and visualization. Teams can share capsules which the model ingests and adapts to collectively, with governance controlling who can consolidate what.
Emerging markets perspective. Low resource languages and intermittent connectivity demand models that adapt on-device. With NL, fast-level updates can be local, mid-level can sync opportunistically, and slow-level consolidation runs when bandwidth permits. This could shrink the gap where static models fail under dialectal variance.
Privacy-wise, on-device fast-level learning is attractive. Compute is local, consent is simpler, but you still need federated proofs of deletion and differential privacy noise on mid-level syncs. Combined with reputation systems for updates, you can keep adaptive systems compliant. One subtle insight, NL reframes depth. Adding layers doesn't necessarily add computational depth if updates don't alter how the model compresses context. Increasing levels, distinct frequencies, adds a dimension of learning capacity that classic depth alone misses, which explains why some deep models fail to adapt despite huge parameter counts.
Which is why I like the heuristic: depth for representation, levels for learning. Just be careful not to conflate more levels with better performance. Without good inner objectives and schedules, you just add noise. That's why inner objectives matter. Dot product is easy but can lead to Hebbian saturation. L2 regression with delta rule trains the memory to allocate capacity efficiently, and gating plus normalization control scale. Combine those and levels become additive rather than chaotic.
Monitoring stack, 3 tiers: adaptation metrics, time to first update, retention, stability, variance post-update, and safety, drift against policy. Each level logs its contributions and we visualize them together. This is where observability kills bottlenecks, as noted.
For stakeholders, we define success beyond static benchmarks: adaptation speed, cumulative reduction in rework, and error recovery rates. Teams care if a system rebounds fast after a bad update, not just that it's accurate on day one.
Competitive differentiation comes from offering learning policies as products. Clients choose their cadence and governance and get a predictable adaptation profile. We've seen organizations outperform by combining faster adaptation with safe consolidation, not merely by chasing larger models.
Last caution, goal drift can creep in unnoticed. Periodically validate that high-level objectives still hold and embed human-in-the-loop sign-offs before promoting slow-level updates in regulated workflows. Think of it as clinical trials for memory.
And if I may, a quote to ground us. William James said, "The art of remembering is the art of thinking." NL operationalizes that. Compressing context is not rote storage, it's structured thinking across timescales.
Before we wrap, give me a concise adoption blueprint. What would you advise a CIO or head of AI to do next?
Start with a pilot where fast-level learning augments an existing model. Enable deep momentum with L2 inner objectives and stable nonlinear outputs. Measure adaptation gains and tune gates.
Build the serving pipeline for stateful inference, session-level caches, shadow sandboxes, and rollback tooling. Establish retention and replay policies before turning on mid-level consolidation.
Expose memory controls to users, scope sliders, commit buttons, and memory cards that explain updates. Define UX metrics around smoothness and trust, not just accuracy.
Set governance. Choose learning policies per domain, budget compute per level, and track business KPIs on adaptation and stability. Prioritize 2 or 3 high-impact workflows to avoid diffusion.
Implement compliance frameworks. Consent banners tied to level-specific retention, deletion proofs, and audit-friendly logs. Run red team drills tailored to adaptive updates. Invest in measurement and theory. Run ablations, track surprise signals across levels, and test compositional generalization. Sharpen your understanding of when levels help versus when they interfere.
And please, keep a contrarian in the loop. Question whether each level earns its keep, and watch for overfitting to gradient history. The best systems are skeptical and observable.
That's a wrap. Nested learning gives us a lens and a toolkit to move beyond static stacks toward models that learn across time. Hope shows early evidence that deep optimizers and continuum memory can deliver both technical and business gains, provided we respect the governance, measurement, and deployment realities. Thanks for joining us, and we'll see you next time. Before we sign off, here's the end-to-end wrap. Nested learning reframes models as layered, context-compressing memories ordered by update frequency. Optimizers become learnable associative modules. Continuum memory adds timescales, and Hope operationalizes all of this with dynamic projections and multi-level MLPs, delivering better perplexity and reasoning while enabling continual learning with governance. Theoretical highlights: formalizing components as associative memories. MKV with local surprise signals clarifies where adaptation occurs. Ordering by frequency explains multi-order in-context learning. Open questions include convergence with interacting levels, identifiability when compressions overlap, and expressivity gains as levels grow, each of which offers testable predictions.
Technical innovations. Deep momentum as an MLP memory, L2 inner objectives and delta rule for capacity allocation, Newton-Schultz stabilization to keep fast weights sane, dynamic KVQ that learn update rules, and interference mitigation via learned gating, orthogonalization, and chunk-aware normalization. If you build one thing next, make your optimizer a first-class memory with a stabilizing nonlinearity.
Deployment essentials: stateful serving, shadow sandboxes for self-modifications, replay-driven consolidation, rollback and deletion propagation, and tiered scheduling, fast per token, mid per chunk, slow offline. Keep P99 latency in check with session caches and checkpoint prefetch, and make long context feasible with shard eviction and causal logging.
Product takeaways: expose memory controls, scope sliders, commit buttons, memory cards, define learning policies per domain, and measure success with time to adapt, retention, and error recovery rather than a single accuracy number. Ship domain templates so teams can choose fast only, fast plus mid, or full continuum modes.
Strategy lens: adopt in phases, targeting workflows like support, coding, and personalization where adaptive gains compound. Differentiate by offering learning policies as a product. Budget compute per level and track reductions in rework, escalations, and cycle time rather than chasing bigger models alone.
Safety and compliance, provenance and consent per level, deletion proofs with replay-aware masks, quarantine gates for fast updates, red teaming of adaptive behaviors, and audit-friendly schemas capturing gradient magnitudes, surprise signals, and update origins. Add DP noise to mid-level syncs and require human sign-offs for slow-level promotion in regulated settings.
Contrarian wrap: observability is the bottleneck. Invest in per-level metrics first, run ablations that isolate optimizer memory depth versus continuum levels, and stress OOS shifts. Ensure each level earns its keep and degrade gracefully to avoid overfitting to gradient history.
Neuroscience forward view: NL aligns with synaptic versus systems consolidation, predicts higher-order in-context capabilities without massive parameter changes, and invites experiments on compositional generalization with replay. Bridging hippocampal cortical insights with multi-timescale training will sharpen both science and engineering.
3 closing takeaways. Design models as nested memories that learn across time, pair adaptive capacity with rigorous governance and observability, and measure adaptation speed and retention alongside static accuracy. Hope shows this is tractable and valuable, and with careful rollout, teams can turn continual learning into a durable advantage. Thanks for listening, and we'll see you next time. Great insights spread fastest through trusted networks. Share this with a practitioner or strategist you respect.